Hello guys, welcome to my YouTube channel. In today's video, I would like to talk about logic gates. Most electrical and electronic students will learn about logic gates in their subjects at college level or university level. Probably you will learn about logic gates on a subject called logic systems and in a subject called digital electronics and digital fundamentals. But logic gates are also the fundamental building blocks of PLCs, which is programmable logic controllers. In electronics, when we talk about logic, we talk about circuits that when you design your circuit, you want to achieve a specific outcome, but you want to be able to control that outcome. Let's make a simple example. You want to start a pump, but you want that pump not to start if certain conditions are not true. In that case, you will use something like a logic gate. There are different types of logic gates that we're going to talk about today, but I was just giving you an overview of why there are logic gates. So you want to manipulate the output by changing the input. So the basic type of a logic gate is a NOT gate. Here is the symbol of the NOT gate. This one. A NOT gate is a type of a gate that will give you a high output when its input is low. So we're going to be using three words here. We're going to be using high and low. We're going to be using true, odd, and false. And we're also going to be using a 0 and a 1. So in a NOT gate, if the input is low, the output will be high. If the input is a 0, the output will be a 1. If the input is false, then the output will be true. This is a type of an example. When you say if the input is low, let's say if my switch is off, I want my lamp to come on. It's a NOT, it's an inverting. Because on a normal circuit, you will expect that if I give you a high input, which is if I make my input on, then my output must also be on. But a NOT gate does not work like that. It's an invert. It's a reverse or inverse of what is known as standard. Okay, but I hope it's clear. Now, these are very important. There will be situations when you design circuits whereby you want the output to be the opposite of the input. You want when something is not happening to trigger something. Just in a simple example, an alarm. I want when something, let's say when my switch is off or when something is off, I want my circuit to warn me. So in that case, you'll use an inversion. Okay, but not dwelling much on the NOT gate. Let's move on to the NAND gate. An AND. Let's start with an AND gate. As you can see, the words AND explain themselves. An AND gate is a type of a gate or a logic gate that will have at least two inputs. So in an AND gate, let's just move this a little bit. In an AND gate, I will have two inputs, two or more, but I want my output to be true when both my inputs are true. So if input 1 and input 2 is true, if 1 and 2 is true, then I want to get my output to be true. If input 1 and 2 is on, my output will be on. If input 1 and 2 are 1s, my output will be a 1, and so on. A NAND gate will just be an opposite of that. We're going to look at the truth table shortly. So I'm not going to dwell on the NAND gate because it's an opposite of an AND gate. The third gate I would like to talk about is an OR gate. OR gate, as the word is OR. If input 1 or input 2 is true, my output will be on. If input 1 is on, my output will be on. If input 2 is on, my output will be on. If both my inputs are on, my output will be high. It's an OR. It's a situation whereby you want one condition or the other condition to be true. It's not necessary for both conditions to be true, but if one of them is true, then you get an output. You can have an example of a circuit like this. Let's say you want, if one of the two valves are open, my pump can still pump. So valve A or valve B can be open, the pump can run. But if both are on, my pump can still run. But if both are off, then my pump will not run. Then again, the NOR gate will be the opposite of the OR gate. Okay, let's dwell bitly on the XOR. There's a gate called an exclusive OR gate. An exclusive OR gate is a type of a gate that is exclusive. Being exclusive means it looks at both your inputs, and if they are the same, it will give you a certain type of an output. With an XOR gate, if I get this input 1, if this is 0 and this is 0, it will give me a 0 output. Off gives me an off. But if this input comes on, it gives me a 1. If both are true, it still gives me a 0. So the exclusive OR, it wants my inputs to be different. So in a sense that if both of them are true, it will give me a false. But if one of them is on, it gives me, let me just bring in the truth table so that this one can be clear. Let me bring a truth table. This is the truth table of an exclusive OR gate. So if you have a 0 and a 0, you get a 0. If you get a 0 and a 1, it gives you a 1. A 1 and a 0 is 0, but if both are true, it's still 0. This other line is for an exclusive NOR. So each gate has got a partner. You've got an AND and an NAND. You get an OR and a NOR. You got an XOR and an XNOR. Then you get a NOT gate. Okay, fine. While we're still at the logic gates, at the truth table, let's just look at the other truth table shortly. This one, it's a NOT gate. Like I said before, NOT gate, if my input is 1, I get a 0 output. If my input is 0, I get a 1. Okay. The AND gate, if you get if my input is 0, 0, I'm getting a 0. 0 and 1, still a 0. So both inputs, it must get a 1 and a 1 to get a 1. Then this other truth table speaks to the NAND gate. Again, OR gate, 0 or 0, I'm getting 0. 0 or 1, I'm getting a 1. Okay, but I brought this circuit to also give you a short demonstration of what I'm talking about. In front of us, we've got an electronics trainer. This electronics trainer, you can simulate or connect these logic gates practically and see how they work. Okay, this component here is a type of an IC. I did speak about IC on my other video, integrated circuits. This integrated circuit they have built-in logic gates. The one on the side, it's an OR gate. It's a 74LS32. You don't have to grab that value. You can just, by looking at the number on the IC and going online, looking up online, you will find that, okay, this is a NAND gate, this is an OR gate, this is a NOT gate, and so on. But in the past, we used to go to data sheets. Before the internet was like this, you would go to a data sheet, and then the data sheet would tell you, it would have all the list of electronic components, something like this. Then it just explains that if your IC has got this type of a number, then this is the way you're going to be wiring it, and this is a type of logic you'll get out of it. Okay, so now let's just test the logic I just spoke about. So since we said the one on the left, the one on the left is an OR gate. So this is an OR gate. So the pin layout or pin number, the pin numbers, you count them from this side to that side. Okay, so after this U-shaped groove, the first pin is pin number 1, pin 7, 8 till pin 14. So we already know that pin number 14 is reserved for plus VCC, which is positive voltage. So I connected that to the positive voltage. And then pin number 7 is reserved for ground. You see here, I connected it to ground via this wire. Okay, now that is just to power the IC. Then my datasheet tells me that pin number 1, 2, and 3 are reset, meaning pin number 1 and 2 are the inputs and pin number 3 are the outputs. So I connected these two wires to the input, which is my input this time will be the switch. So these are the switches. When I switch these switches on and off, I'm expecting to manipulate the output. At this point in time, my switches are off. They are in their off position. So when I push them to this side, I'm going to be making them on. I want to see now, will the OR gate do what it's supposed to do? This LED is my output. So it can be anything, meaning in the real world, it can be a pump, it can be a valve, it can be a lamp, it can be a buzzer, it can be a lot of things that you can be controlling. But then I want to see if the OR logic works. So we said in the OR gate, if one of the inputs are true, the output should be true. So let's test that. So I connected input 1 and input 1 and input 5 if you look at this one. So now let me make just one input 1 on. Input 1 is on, back off. Okay. If I make input 5 on, input 5 on. So when 1 or 5 is true, my outputs come through. If both of them are true, my LED stays on. But when both of them are off, then my LED comes on. So that proves that the OR gate is doing exactly what it's supposed to do. Let's move on to the next gate, which is an NOR gate. This one. This is a NOR gate. A NOR gate should work more like opposite of the OR gate. I'm just going to move the wires to that side and then we test it again. Alright, so I've moved to the NOR gate. The NOR gate, according to my truth table, here's my truth table of an OR gate. So the NOR will be this one. So my NOR gate will only be true when both switches are off. 0 and 0 gives me a 1 in a NOR gate. Remember, this logic is for an OR gate. This one is for a NOR gate. Now, both my switches are still off. The output is already on. If I make one of the switches on, let's make this one on, my output goes off, just like that. And then if I make both of them on, both my inputs, my switches are on, output is still off. And then if I make, let's say, input number 5 only on, still off. So for a NOR gate, I need both inputs to be off to get a 1. Exactly what we are seeing now matches exactly what the truth table tells us. Okay, let's move on to the third gate. According to our list, the third gate should be an XOR. XOR gate is this one. An exclusive OR gate. Here's the truth table for the exclusive OR. Let's just move the wires to that side and check. Move the wires to that side and check. Alright, now we are on the exclusive OR gate. At this point in time, both my inputs are 0, which is my switches are off, off, and I'm getting an off. My lamp is off, which is good. Now let's make one of them on. Let's start with number 1. If I make one of the inputs true, I should be getting a true. That's correct. Now let's make both on, which is number 1 is already on. Let's do number 5. Now, when both inputs are on, which is 1 and a 1, a 1 and a 1 gives me a 0. It matches the logic. And then let's make just number 5 only on. If I make number 5 only on, so an exclusive OR is looking at both inputs, and if they are the same, it gives me a 0. If the inputs are different, it gives me a 1. That's exactly what an exclusive OR gate should do. Let's move on to the fourth gate. I think it should be the fourth gate should be an AND gate. AND gate is the one, I think it was the second one when we were explaining. Let's just look at this logic again. AND gate, both inputs must be on. Okay, fine. Let me first change just the wiring to move to the AND gate, which is it's gonna be this one. I'm gonna shift a little bit to this side. Okay. All right. We've moved the wiring now to the AND gate, which is this side. Fine. All right. Now, my two inputs are zeros, which is they are off. If my switch 1 is off and my switch 5 is off, I'm getting an off lamp, which is good. Then let's just switch on one input. Input 1 comes on, still off. Okay, that matches the logic of an AND gate. Matches the logic. 0 and 0 gives me 0. 0 and 1 gives me 0. Let's do the other one. Try to switch the second switch. If we do this one, again, 1 and a 0, I'm still getting a 0. But if both are on, which is, if both inputs are on, which is a 1 and a 1, I'm getting a 1. So this matches the circuit again. So these ICs are very useful in testing this logic gate, and I think it's very useful when you are still studying these things to experience them, because to learn about the theory about them and to cram how the gate works is not very beneficial. But when you begin to experience or see them, how they are really working in a circuit, then there's no way you'll forget it, because once you have that personal experience about this thing, then it sticks to your mind forever. And then now it's no longer a matter of cramming, but it's something that when somebody talks about a NAND gate or an AND gate, your mind automatically knows what it means, because you've seen the logic working in a practical way. Okay, let's test the last gate, which is the NAND gate. I'm expecting this one to be the opposite of the AND. Okay, we're just gonna move the wiring to that side. So pin number 3 is located for the output. Pin number 1 and 2 are your inputs. Okay, it's got sets of inputs, but I just used the first gate. It's got many sets of inputs, but I decided to use just the first gate on all these circuits for simplicity. Okay, now, so this is my NAND gate. Remember, I forgot to switch these things, but both my inputs are true. 1, 1. I'm getting 1, 1. So my NAND is giving me a 0. Let's see now. If I'm giving them, let's say a 1 and a 0, I should get a 1. A 1 and a 0. So this is a 0. This is a 1. I'm getting a 1. Okay. Let's move on. A 0 in the, okay, let's just go with the steps. We said a 1 and a 0. Now we're going to say a 0 and a 1, which is this one goes to 0. This goes to 1. Again, 0 and a 1. My output is still on. And then a 0 and a 0, meaning both switches are off. 0 and 0. I'm still getting an output that is true. So this matches the NAND gate. So the only time a NAND gate will be false is when both inputs are true. Both inputs are true. Sorry. Both inputs are true. And then I only then I'm getting an a low output. So this is basically a very useful digital trainer that you can probably buy from an electronics store to teach your young children or the youth who are interested to learn electronics about logic gates. You can actually use it for many things. It's got these switches which are you can use as your inputs. It's got these LEDs which you can use as your outputs. I only chose to use a separate LED because when I was testing my circuit, these LEDs were not glowing so brightly. So I thought maybe in the video you won't see it. It won't be easy for you to see it. But you can use these ones as well. This is a very useful circuit. But coming back to the topic that we're talking about today, we covered a NOT gate. We covered an AND and a NAND gate. We covered an OR gate and a NOR gate and an exclusive OR gate. So in this video, we covered some important logic gates, which is your NOT gate, your AND gate, and the NAND gate. We also covered the OR gate, the NOR gate, and the exclusive OR gate. These are very important gates to understand, and they are the fundamental building blocks of programmable logic controllers. Once you understand these gates, when it comes to PLC programming, then you'll understand some of the circuitry and the logic that is being used there. Because even in a PLC, there is an output that you are trying to switch on or to control based on the conditions of the inputs. So if input A and input B are in a specific condition, you want to achieve something on output so and so. Thank you so much for watching the video. And please do like the video, do share the video with anyone who will find it beneficial, and do subscribe to the video so that you can continue to grow and share this kind of educational videos. Thank you for watching. Enjoy the rest of your day. Goodbye.